Good morning, and welcome to the session, The Oceans and Their Properties. I am Georgios Haralabous from the IMS division, and I have the pleasure and the honor to co-convene this session with Dr. Silvia Blanc from the Argentinian Navy Research Organization. Silvia is the first woman that was, first researcher that was hired in this organization. We have three very interesting talks about T-waves, bathymetric effects, long-range propagation, and without any further ado, I would like to ask Silvia to present the first presentation.
Okay. Good morning to everybody. Here I invite now Mr. Vaibhav Ingale to come for his oral presentation about detection of T waves associated with mid-ocean ridge seismicity, recorded by hydroacoustic networks, manual versus automatic approaches. So, thank you very much. Please.
Thank you. So good morning, everyone. So today I'm going to present about how can we understand the hydroacoustic signals and how to detect them manually, and what could be the perspective to have a automatic detection approach. So in this figure, as in the top right, as shown by the thick black lines, are the mid-oceanic ridges, which are the long range of the volcanic mountains formed by the plate divergence, which is shown by the animation at the bottom left. So because of this divergence as well as the magmatic activity altogether, it produces large number of small magnitude earthquakes. But such mid-oceanic ridges, they are very far from the land-based seismic networks, and due to the rapid attenuation of a seismic waves, we are not able to monitor such seismicity. So there is another approach used by the ocean bottom seismometers to detect these small magnitude events, but such surveys are for the very short scale as well as for the very short duration of the time. So here comes the interesting fact about the hydroacoustic experiment, where the seismoacoustic waves are generated from the seismic to acoustic energy conversion, and these events travels over the longer range, which are shown by these blue lines through the SOFAR channel, and using those T waves, we can able to understand this seismicity. Having said that, we have deployed a hydroacoustic network in the Indian Ocean, which is called as Oasis Bio Network, and it records the signals at continuous sampling of 240 hertz. This network was active from 2010 to 2023. Along with this, we also have used the hydrophone data from the IMS stations placed in the Indian Ocean, as shown by these blue squares. So combined network, it helps to monitor not only the seismic activity, but also the marine mammal activity, as well as the cryogenic events down in the southern Indian Ocean. So based on the hydrophone network, here I show one example of a T wave recorded on the different hydrophones. So the bottom right figure shows the enlarged view of the first channel, like in the 30-second, in the 30 minutes window with the range of 0 to 60 hertz. We can clearly distinguish between the P, S, and the T waves, T for the hydroacoustic T waves. But as we see in the first figure, these P and S seismic waves, they don't travel over the longer distance with respect to their attenuation. Uh, there is another type of a wave which is called as a H wave or the volcanic or the impulsive signal. So it is very short, showing sort of a delta function feature. It is a short duration and it reach up to the 60 hertz frequency range. And such waves also travel over the longer distance. So our interpretation says that these waves are generated by the hot lava and seawater interaction on the seafloor. But analyzing this hydroacoustic data manually, it takes a lot of time, and the efficiency, it also varies from one user to the another user. So here I show my perspective example of the manual picking of earthquake and why do we need to have an automatic approach. So along the southwest Indian ridge, which is a ultra slow spreading ridge, in the second figure, we observed some seismic cluster based on the land-based seismic ISC catalog shown by the green circles. And the white circle shows the moment tensor solution associated with few of the earthquakes. And the red dot are shown the hydroacoustic detections. If we compare the number 250 land-based network versus 27,000 hydroacoustic events in the period of 10 months. So that detection threshold will help to understand the minor aspects of the seismicity. And apart from this hydroacoustic event, we also have detected the H waves or the impulsive event in the same region. They are mostly located between the fracture, the transform fault boundary shown by this black dashed line and the bathymetric heights. So this manual approach was done in the 2 iterations. So in the first iteration, you detect a signal on the one particular hydrophone shown in the first panel, and then scroll the data to get the same signal on the rest of the hydrophones to locate and to compute the event in terms of location, origin time, and the magnitude. And in the second iteration, use this information to zoom the window by 3 times, so that we will able to distinguish the correct T wave picking to have the proper exact location as well as the origin time. Why there is a need to do the 2 iterations of picking? So the first panel shows the error in the location and the origin time. The red and the black histogram shows the error in the location, which is around 3 kilometers, and origin time in the error is around around 1 second. But in the second iteration, using the zoom time window, this error improvements less than 400 meters in the location and less than 0.2 seconds in the origin time. So this will give the proper constraint on the volcanic event or the seismicity. But here is a catch. Doing this same amount of work in the 2 iterations of picking took around 131 days, assuming 8 hours of a continuous work during the working days. So just to detect the event, it takes around more than 4 months. Sometimes it invests a lot of time. If you have a large number of seismicity, then it will take forever. So this is the time that we need to develop some automation algorithm. So for this, we are using the convolutional neural network based on the autoencoder AI tool. So in the first case, we detect the positive spectrograms based on the manually picking data showing the impulsive signatures, and the rest of the data is considered as raw data or the negative waveforms. And then we train the algorithm so that it will extract the impulsive signals based on the given frequency range and the duration of the signal and the probability distribution. So having said that, we can have a different families of the impulsive events on the one stations, and we can cluster them together to get a more sample space to train the model. After having such number of detection, we can train the detector for the given frequency range and the time to use those detectors for the continuous data set so that we can extract the informations from the available continuous data. But based on this and having the probability distribution, there could be a chance of recording the seismic airgun shots. The first figure on the left shows the spectrogram of the airgun shots showing the similar characteristics of the volcanic signatures. And the bottom panel shows the probabilities distribution. It shows the harmonic nature with the periodicity. But these events are easy to remove because of their short-term periodicity and the probability distribution. And on the right, it just shows the one example of how this seismic airgun shot experiment is being performed. So after removing these seismic airgun shots, then we try to verify those events manually to check the true positive event detections to obtain the hydroacoustic catalog specifically for the volcanic events. So we have trained this model not on the larger scale, but on the smaller scale near the Mayotte Island in the Indian Ocean, where the right figure shows the region with the 4 hydrophones shown by the white. And there was a volcanic eruptions which was recorded on the 4 hydrophones. So our model training has been applied on this data set, and we were able to detect the events with a very efficient manner. Based on its arrival on the spectrogram, we can readjust the time as well as the position so that we get the accurate location and the origin time of the event. So after the training, after the human verification, there is one more catch, is that sometimes we may able to confuse between the natural volcanic event versus the artificial or controlled source experiment explosions. So in the spectrogram window on the left, it shows the spectrogram for the natural volcanic event recorded originated in the Indian Ocean, having the duration of around 10 to 15 seconds with the frequency reaching up to 60 hertz, and which is shown by the blue arrow. And there was a control source experiment performed off West the Argentina in 2017 to monitor the lost submarine. There we also on this station near in the Indian Ocean, the hydroacoustic river recorded showing the similar frequency content and the duration. So we also need to understand and train the model to distinguish between the natural versus the artificial events. So in this case, the data preparations, extracting the signals from the manually picking to store them as positive spectrograms of the volcanic signals, then training the model to detect the signals from the non-analyzed data, and then excluding the natural, excluding the seismic airgun shots or the artificial explosions. Then, and after human verifications, we can able to build the algorithm and to make the catalog of the events. So with this improvisation, it has been observed that we can able to detect around 280 events per hour versus just 26 events of the 26 events per hour of the manual work. So this automation technique is helping to understand the seismicity on the larger scale and with the efficient manner. So on overall approach, it has been observed that the hydroacoustic network helps to understand the seismic event with a well-constrained location and the time. We can able to distinguish between different type of phases like the T waves from the earthquakes or the H waves from the volcanic events. But the manual picking takes a lot of time and its efficiency varies from user to user. But the automation is helping to get one step ahead with the maximum number of detections within a given time. And like this efficiency has shown like that we can able to detect around 70% of the true volcanic events with a given data set. But this approach is based on the impulsive signals of the volcanic, and we will try to extend it to the T waves, which is the real big task, because T waves have a long range propagation effects with the bathymetric obstruction as well as the dissipation in the over the long range. Thank you so much, and I'm welcome to the questions.
Thank you very much for the presentation, and we invite you to make any question. We have a short time, but we can have one or two. Yes. Yes, Mario.
Very nice presentation.
Mario, microphone.
Very nice presentation, very interesting. One question that I would have is, do you have any statistics or experience with the discrimination between airgun shots and volcanic signals? Like when the algorithm rules out or eliminates airgun shots, does it also tend to eliminate by the same logic volcanic sharp and short duration volcanic arrivals, or is it possible to distinguish there?
So in our data case, it has been observed that the volcanic signal, their frequency of the arrival is very different compared with the seismic airgun shots, because the volcanic arrival showed the different variation in the probabilistic distribution based on the ground truth. And the seismic airgun shots, because it's a control source experiment, we have the similar probabilistic distribution of an arrival. So that becomes easy to distinguish between the both type of events. I hope it's clear for you.
Thanks, clear.
Another question? Okay. So we thank you very much.
And we move to the second presentation by Juan Gonzalez from the Acoustic Propagation Department of the Argentinian Navy Research Office. And the title of the presentation is Analysis of Bathymetric Effects of Long-Range Acoustic Propagation using 2- and 3-dimensional transmission loss models in signals generated by airgun arrays.
Would you like to address it? Yeah.
Juan?
Yeah, thank you very much for the introduction. And I need... Yes.
That is not a point.
Okay, yeah. Thank you. Okay. Okay, thank you very much again. First of all, I say sorry. My English is far from being good, so I will try to do my best. But the background of this contribution is fundamentally associated with, first, the unfortunate loss of Ara San Juan submarine a few years ago alerted us about the value of hydroacoustic signal records acquired and stored by INS and IDC at CTBTO. And second place, first attempt to validate acoustic long-range propagation models with signal data received by CTBTO Hydroacoustic Station was presented at the previous conference 2 years ago. Its motivation is essentially the challenge of addressing ocean acoustic modeling for realistic environments when the sound sources are directional like airgun. Our goal consists in using 2-dimensional and 3-dimensional long-range propagation models in order to improve the understanding of the bottom acoustic interaction near the source due to airgun shots using signal data registered at the CTBTO Hydroacoustic Station. And finally, an important warning is that the work that we are presenting is a work in progress. As regards modeling transmission losses, we first use the two-dimensional model RAM 1.5, and currently we are using the 3D split-step Fourier method, originally developed by Wai-Chi and others, and we are going to focus on this on this model. Let us make first give a brief overview of the 3D split-step Fourier method by Wai-Chi. So the governing equation in frequency domain for the acoustic pressure P is given by equation number 1, but by doing a special transformation suggested by Bergman, one obtained this kind of equation that is an Helmholtz type equation, which defines an effective refraction index that has correction that depends on their derivatives, depends on rho, the density, and their derivatives. So as in ocean acoustic, the density profile is discontinuous, a procedure called interface smoothing is applied that consists in replacing the density profile by a continuous expression. Well, and if the parabolic approximation is used to solve the equation of the Helmholtz time, then it's important to bear in mind the following 4 points. First, we need, this is a theoretical thing, we need an expansion of the square root operator. The method follows a specific proposal that allows numerical solutions that follow a marching scheme based on a two-dimensional FFT. And here we can see the how is the marching scheme. In each screen, we have the values of their effective refraction index. And then the X are the propagation direction, and transverse X are the YZ coordinate that can be thought in each screen. So to compute this equation, the method is split this evaluation into 2 stages. The first stage accounts for diffraction effects only, and the second stage takes into account inhomogeneous effects from n squared. Without providing more detail here, we can say that the FFT is used in the first stage. Another details about this method is that, well, to satisfy the pressure release boundary condition at the sea surface, an image acoustic field is applied, and second, an artificial absorbing boundary condition is used to avoid spurious reflection from the boundary of the computational domain. Well, let us now see the 2 types of result we obtain. First, on one side, we developed an efficient implementation of the algorithm for realistic oceanic scenarios with input data taken from SHEPCO, the bathymetry, and Copernicus for the environment variables. And it is important to say that we did it on the basis of a MATLAB code for the Lloyd mirror pattern publicly available. And on the other side, we applied the implemented 3D propagation model to analyze signal data from airgun shots registered by CTBTO hydroacoustic stations. Regarding the model implementation, we used the Juliac programming language that can run efficiently both in multi-core CPUs and GPU through CUDA. Well, running the code on GPU is faster than doing it in CPU, but it's more memory limited. So the key observation is that we calculate the effective refraction index directly on the GPU by interpolating from source data preloaded onto the GPU. What we did is to take the Copernicus data that has low resolution and the data is light, so we can send this data into the GPU and then refine into the GPU without sending data between CPU and GPU. And as a result, we have an implementation of the model that is very fast in comparison with doing it in CPU. And however, it should be kept in mind that the real bottleneck comes from the screen grid itself and the delta Z and delta Y. Well, in this slide, before any attempt of applying the implemented model, we verify our implementation against previous published results. And as it can be visualized here, quite satisfactory results were obtained in a first comparison, especially considering that we have different data sources. In the paper for 1,000 kilometer propagation path, they use this different data simulation system. Well, here the following the simulation facilitates the visualization of transmission loss as a 3D acoustic fields. Here we are showing how it's works for different parallel set planes. In this picture, we can see the transmission loss for transversal-wise setup planes. Here we schematically show how the numerical methods builds in the whole 3D scenario. And this is for Y constant planes. Well, let us now try to discuss some concluding remarks, highlighting which is the current situation and the plans for coming work. We are focused on, the verification of the transmission loss prediction should be improved by comparing it with a benchmark solution. We didn't do it yet, but well, it's for coming work. And finally, I would like to say that that GPU implementation is not suitable for high frequencies or very wide screens. Currently, the code can handle problem with the screen width 1,000 kilometers and cell dimension, the delta set of about 10 meters, by using a 6 GB GPU. Some improvement can be made at the cost of some performance. Well, as regarding the application to Airgun shot signal registered by CTBTO, a large two-dimensional offshore seismic survey was carried out in waters of the Argentinian coast. We know the dates, locations, and configuration arrays of this experience, and so a routine was developed to detect the signals generated by the Airgun array seismic source at H10 station. Here we have an example of the analysis signal in time and frequency domain. Then, well, the recorded pressure levels at Hydroacoustic station H10 node was analyzed, and energy spectral density were estimated. On the other hand, the source level of the Airgun array was estimated using Agora software, and here we show its spectral signature. Well, in this slide, we are showing the comparison between the two-dimensional and three-dimensional propagation models. On the left, we can see the transmission loss for different depth theta, and the two-dimensional and three-dimensional models along the propagation path, the geodesic path. On the right, we are showing the bathymetry and the 3D split step Fourier model results. And finally, we are on the bottom, we are showing the comparison between the two-dimensional and three-dimensional model at H10 position. Well, as conclusions, well, the results obtained with two-dimensional and three-dimensional models shows relatively slight differences for transmission loss. However, in frequency domain, when comparing transmission loss predicted by both models at hydrophone station, they differ about 10 dB for frequencies greater than 7 Hz. And well, the forthcoming work in progress will deal with the following issues, especially in order to validate 2D or 3D models with IMS registered signal of Airgun shots. source level for the Airgun array should be previously revisited. We are using the Agora software, and we would like to have a better modeling for this situation, especially to consider the pressure values at the first screen and start our propagation method from that. Well, last, this is the real-time execution for the 1,000 kilometer propagation path. It took us 79 seconds. And well, in each screen, what you are seeing is the computation of the effective refraction index, the marching step through the FFT, and the plotting the data. All these things are made into the CPU. This is a kind of purely GPU implementation. We use Julia and the Mackie library to plot with GPU functionality. Well, thank you very much for hearing.
Thank you very much. We have time for 1 or 2 questions. Yes, please.
Thank you very much for your nice talk. Actually, I'm not making a question, but a kind of comment. I'm a co-author of Whited about the paper of parallelizing his code. And I think that having 2 versions of the same implementation is not that good, and probably we can merge our efforts onto one single code. And if you are interested in please give me a minute to talk about how we can merge our efforts onto a single code.
Yes. I'm sorry, I couldn't understand the question.
Just a comment.
Okay. Okay,
Yeah,
thank you.
That's a comment.
You can discuss afterwards. It was, yeah.
Okay.
Thank you
Thank
very
you.
much. Any other question and comment? Kevin?
Yeah, thanks for the talk. Do you know the...
Wait, so people can hear you.
Thanks for the talk. And seismic air guns are certainly a large part of the ocean soundscape on the CTBTO system. Do you know, I see you have the track of the actual ship survey over the whole bank do you know the laydown of guns and the orientation of them for modeling the source level? Because Ogora, I believe, is for a single gun, and then you have to build it, source level model with the whole array.
Sorry, I think I can help in this question because I'm more related to the physical part and so on. Yes, we have information, which is not so easy sometimes, about the particular data, which are perhaps not the more convenient, because they don't show a relevant difference between 2D and 3D. But in this case, we have the information. And the extension of Agora that was used, in a way, consider the array, the actual array with a number of sources in each stream. So that's right.
Okay, thank you.
Thank you.
Thank you.
Oh, now, I'm inviting with great pleasure Dr. Tiago Oliveira to talk to us about T-waves from Kermadec earthquakes acquired by CTBT hydrophones. Thank you.
Thank you, Sylvia, Georgios. Good morning, everyone. So we will keep talking about long-range propagation in the ocean, but after the previous talk, it was more numerical, model focusing. Here we go back to more data analysis. So here we have the list of my colleagues that collaborate on this study. And here we have a map of our hydroacoustic network, IMS network at CTBTO. And you have with the stars, you can see the location of our hydrophone stations. And let me see if I can point. It's not easy, but here. Okay, so here we have HO3 that is in Chile. And in this talk, we'll focus on the signals received at this station that are coming from Kermadec earthquakes. So Kermadec is here where you see that red line. And it's a very active area. We'll see that later. So we have here some schematics of our hydroacoustic station. But in this plot in the left bottom, so you can see that, for example, we have a triplet of hydrophones in the north of an island, and a triplet of hydrophones in the south of an island. In this case, is in Robbins Crusoe Island. So this is to take in account that when we have, for example, sound coming from the north, if we have an island and our hydrophones are in the south, so we have some shadow. So that's why we have two triplets of hydrophones in our stations. So here you have a map with the events in LEBs. Maybe if some of you are from NDCs, you are familiar with these LEBs. So these basically are bulletins provided by CTBTO. So in this case are events reviewed by our analysts. And it's just for you to have an idea. So these events that are different from detections. I will explain later on what's a detection. So these are from 2014 and the end of 2022, so 9 years. And you can see that most of these red dots are in very active seismic areas, including the ring of fire in the Pacific Ocean that, well, here is carried in this map, but you can see that HO3 station is close to the epicenter of most of these earthquakes in the ring of fire. So before was our events that are built with all of the IMS networks, seismometers, the infrasound network, and hydroacoustic network. And now here I'm showing only the contributions from the HO3 station, from the north and the south array. And you can see that most of the contributions are coming exactly from the Pacific Ocean and around the Ring of Fire. And here's like a more detailed analysis and for the type of phases that these stations are contributing. So you can see that most are T phases. We saw in the first presentation a good explanation of what a T phase is. And we also have some P phases. We also saw what a P phase is in the first presentation. But if you pay attention, you see that most of the P phases are coming from Chile, just because it's close to the station and they don't lose that much energy. So what I want to say with this is that, yes, we get a lot of T phases coming from the Kermadec, but we don't get P phases just because they lose energy propagating in the bottom. And then we have some H phase events, as we saw before, for example, seismic surveys, also detection. But we have here also some numbers for these contributions. So in this presentation, we analyzed 16 strong earthquakes that occur exactly between 2014 and 2022 that had moment magnitude higher than 6.5. So you have in these dots, here you have the location of the earthquakes. You have there the list of the earthquakes. So this is based on the USGS earthquake database. And here you have the time series recorded at this one hydrophone of the south array at HO3 for the 16 earthquakes. You can see, so they are aligned, this time series, by the theoretical T-phase arrival time. And you can see that clearly, that there is a signal there, okay? So And okay, from these 16, we end up only working with 14 because for a specific one, there was one hydrophone that was not working well. And then there was also 2 earthquakes that occur very close in time. And so we just decided not to analyze one of these earthquakes because otherwise you don't know very well if the signal is from one or from the next earthquake. Okay, so here's the funny part. So this is one of the most complex areas in the world regarding bathymetry. So you have, here on the left, you have the bathymetry, and on the right is just a 3D animation of the bathymetry in that area. So you see that you have Kermadec trench. So in here, that is very deep. So you can have water depths up to 9 kilometers. And so here you have a ridge. And in here, this is what I want you to pay attention. We have a seamount chain, okay, that is known as Louisville seamount chain. And in here on the left, you can also see it. Sorry, this is tricky. You can see the seamount chain. So, and our earthquakes are all in here, okay, around near the Kermadec Trench. So last year, there was a paper published that was based in 2 earthquakes on that area, and this case was also discussed last year in the Hydroacoustic workshop with very good inputs from the underwater acoustic community. And in this case, we have 2 earthquakes that happened just a few hours apart, and with epicenter very close to each other. So this is a perfect case for us because we know that the ocean didn't change that much, okay, and the location is almost the same. So, what happened is that when you look to the 2 time series and one the hydrophone, you see that the time series look very, very similar. And then, so on the right, you can of these plots, you can read the back azimuth, the change of the back azimuth over time. And when you compare the 2 plots, you see something that are very similar. For example, here at the beginning, you have the back azimuth going up, then down. Then you have in both earthquakes kind of a signal that is coming from a completely different direction in both cases. And later you also have here a signal that you can see in both earthquakes. So this paper suggests that so we have this main signal here is due to the T phases that are coupling into the water nearby the epicenter, and then we have earlier arrivals that maybe are coming from acoustic signals that couple from seismic waves along this Louisville seamount chain. So it also revealed that we have detections that are reflections from the coast of Chile, and we also have arrivals that are most likely reflections here from the Antarctica Peninsula. So what we decided to do was to look into more detail in these earlier arrivals and based on these 16 earthquakes, okay? So, can you play the video? So this is a specific earthquake in 2020, and I'm showing where the arrivals are coming from for this first part of the signal that you see there in red. And when you plot them, they perfectly fit the Louisville seamount chain. And now I will show you, sorry, can you, one more? Next slide, sir. And with the video. And now I will show where the arrivals are coming from for the stronger part of the signal. And you will see those dots appearing in there nearby the epicenter. This kind of confirms that we can have for strong earthquakes earlier arrivals that are coming from the Louisville seamount chain, and in this plot here on the right, right here. So you have these dot points are the detections from our automatic pipeline, and then you have here on yellow, okay, and red. So in this case, so we have our global associator software that builds the event detect this case. So, and in this case, so in yellow that it's easier to see, we have the one that is in test, that is NetVisa, and that detects here kind of two potential signals. And then our analysts, that you see is this green point, they correct that arrival, and they pick the right arrival that really corresponds to the T phases triggered near the epicenter. But here you can see how tricky it can be to analyze signals that are coming from earthquakes. Okay. So, and now this is just looking into the signal, but at H10. So that it's in the North Atlantic. So, and on this map here, I'm showing the geodesic path from the Louisville Seamount chain to H10. That, as you can see, is a clear path. And the figure on the bottom, I'm showing you the geodesic path from the epicenter to H10. That is blocked by the Antarctica Peninsula. So it's blocked, but this numerical simulation here shows on the bottom that is blocked, but it can go around and diffract around the Antarctica Peninsula and reach our station. However, because of all these changes, it will lose energy. And here we have the signal, okay, at H10, where you can see again the red part is coming from the earlier arrivals from the event, and the green part, the main arrivals triggered by the epicenter. But in this case, because the ones that were triggered near the epicenter lose some energy, when you look into the signals, the ones that were triggered far from the epicenter can be considered kind of the main arrival. Very tricky case to analyze. So basically, yeah, so you see here, so that there was no detection, okay, linked to the main signal. Okay, so this is a summary of our results at this stage. So we grouped these 16 earthquakes based on the location of the epicenter. So we have one here, group A, that is only one earthquake, that was very in the north. So, and we analyzed where the T phases along this seamount chain were triggered, so it's in this area. So here we have a group B that are all located nearby, 8 earthquakes, then group C, and one more in the south. And we start seeing kind of consistent patterns, and we can have T phases trigger in areas that can go up to 2,000 kilometers. Okay, it's a very long, long line, and they can be really triggered far from the epicenter. So, as conclusions, so the recorded signals at HO3 south that is in Chile. For the Kermadec earthquakes analyzed in here, confirm the conversion of T phases from seismic waves far from the epicenter along the Louisville Seamount chain. The length and location of the T phase coupling in this seamount chain depends on the lat long of the Kermadec earthquake. Also, the length of the T phase coupling zone can range between 600 and 2,000 kilometers. Yeah, so the T phase coupling at the Louisville Seamount chain arrive at HO3 earlier and with, in general, less energy than the T phases coupling near the epicenter. However, we saw a particular case, that was the case that I show you, that sometimes the T phases coupled at the Louisville chain can have kind of the same magnitude as the one triggered nearby the epicenter, and this can make tricky to separate which part of the signal are really linked to the source of the real source of the event. So this is something that we want to explore, this type of specific earthquakes, and we are open to receive some suggestions on this topic. And finally, I just want to say that if you want to perform similar type of analysis like the one that we are presenting here, so we can have access to CTBTO data through a VDEC contract, and also having access to the software that we use for this analysis, and also to some codes that we had to develop to automatically analyze, in this case, for example, 16 earthquakes, but now we are ready to analyze 100 or 200 with the scripts developed during this work. And that's all, and thank you for your attention.
We are open, yes, to questions.
Please.
Mario, please.
Yeah, the microphone is coming. Here. Raise your hand, Mario. So that... Oh, somebody has got it. It's okay. It's coming later.
Okay, thank you. It's perhaps very basic question. Can the hydroacoustic data be used to mapping and also then further predict the seismic movement? And then the second, does the number of the monitoring instrument can affect the differentiation between more reliable data and not? It's very basic because perhaps I'm not understand about it. Thank you.
So, can you repeat the first question? I didn't understand the part.
Can the hydroacoustic data, as you mentioned before, be used to mapping and further predict the seismic movement? Because you talk about the data from 2014 to 2022, but then can this data can be used to predict and further the future seismic movement? Thank you.
Well, my reply is that I don't know how to do that, but maybe this data in the hand of good seismologists can be used for that. Yeah, because with discussions with some seismologists, they've been telling me this. Well, if you can predict somehow what's coming based on some tremors, for example. But we know, we have some colleagues here that are specialists on underwater volcanoes. You have one just on your right, you can ask him. And people look, for example, in signals coming from underwater volcanoes, that's possible, to try to understand if a big eruption is coming. So I don't know if we can use that knowledge, for example, for underwater earthquakes. So the second part of your question that is related with the number of sensors that we have. For detections, that means that you have one hydrophone and you see a signal, okay, and you detect something. We can detect a lot of things coming from very, very far away. Then when it comes to build an event, to say, okay, it's coming exactly from there, from this location, okay, normally you need more than one station. We have a very good coverage, but then maybe there are some parts that have a better coverage just because we have more hydrophone stations there than in other areas.
Mario?
Yes, so these examples that you showed, especially Group C, when you have the coupling at 2,000 kilometers from the epicenter, that's very challenging then for association in the processing algorithm. Do you think that you will, for areas where there is regularly and often such a type of seismicity with these effects, derive isolated sets of test cases for NetVisa and advanced for training of an advanced tool like that? Would that make sense?
Yeah. First, let me mention something in here that that I know that is clear for you, but maybe not for the other colleagues. So at CTBTO, we use the T phases not to locate the epicenter of the earthquake. So we cannot do that just because of all this complexity. So we just associate to the event. So we detect the T phase and we say, okay, this is linked to that event. And yes, as I mentioned, this is one, in my opinion, more complex parts that we have in the ocean because of the complexity of the bathymetry. Yeah, but there are other areas where we have hydrophones in nearby some seismic areas that are less complex. And yes, I think that can be done. In fact, I think that Mark did something with that for in the Indian Ocean, for example.
Thank you very much, Tiago. Thank you.
Thank you.
Yeah, at this stage, I would like to invite you. I know I'm standing between you and lunch. I just have one question online. So I would like to ask you if you have any question for any speaker. We have time for one of them. And I will take this opportunity while you're thinking of a question to ask something that came online to the first speaker. So to Vaibhav, there is a question whether what is the accuracy of the automatic method that you presented, and if there is a confusion matrix, basically, to characterize the performance and the classification. Have you done this kind of analysis?
So we haven't yet computed the covariance matrix or the confusion matrix for this, but based on the small data set or the small detection, we have the accuracy of around 70%, we would say, for the positive detection of the volcanic signal.
Okay.
Yeah. Okay.
Thank you very much.
Okay.
Any other question? Any comments? Yes, please.
I have one to Tiago, please. You used very well T waves, no? And you detect it, and you associate not easily to the epicenter or perhaps to a hot spot where there is a conversion of energy. Concerning the Kermadec earthquake, I heard, I'm not sure, that in January of this year there were also some eruption, something like that, but very, very low in comparison with the previous ones, more or less 4.0. Could you detect that, or it is not possible?
So that's also related with one of the previous questions. In our network, we detect a lot of low magnitude earthquakes in the water. So I think that, even like lower than 4.0. But then, and we detect a lot of submarine earthquakes that are not detected by our seismic network.
Of course.
Yeah, but the thing is that if then you want to locate the epicenter of these earthquakes, you need more than one station.
Yes.
Okay, so we detect, but then we do not locate.
Okay, that's good.
Most of them. But in some cases, yes, you have information. For example, in the Indian Ocean, you have a good coverage, and you have small earthquakes that you detect and you can locate.
Thank you so much.
Thank you very much. One last question came, and it was, how big is your training data? Most likely, it's referring to the first presentation.
Can you repeat the question?
How big is your training data? That's the question.
The training data, like we have the 6 months of recording on 4 hydrophones in 2020 and 2021. So that is the training that we are performing now, but we would like to extend the same training for the data available from 2010 to 2023 for the large area in the Indian Ocean.
Thank you very much. That concludes this session. Thank you very much for participating. Let's put our hands together for all of you participants and the speakers.